Okay, students, welcome to Chapter 17, entitled Alcohols and Phenols. And for this first video that I'm going to post on YouTube, I'm going to discuss sections 17.1 through 17.2. And then after that, I'll make a second video for the subsequent sections of this chapter. Now, if you look at the title, Alcohols and Phenols, you should be familiar with at least some fundamental aspects associated with those functionalities. You may recall that an alcohol is characterized by having an sp3 carbon with a hydroxyl group. Okay? So it's important in terms of being an alcohol that this carbon is actually sp3. Okay? Any other hybridization, it would not be an alcohol. Similarly, phenols, you may remember, are compounds that possess this entire molecular structure. You may recall from chapter 16, this is one of those that you needed to commit to memory. And so phenol itself is characterized by a phenyl ring with a hydroxyl group. And the carbon, of course, that bears the OH is sp2. Okay? And so if you've got this portion of the molecule, even if you have different R groups and halogens all over, it would be considered a phenol. Okay? Now, the first thing we want to do in this lecture is to discuss aspects associated with nomenclature of alcohols and phenols. But before we do that, let's remind ourselves of some fundamental aspects associated with that. You probably recall that alcohols can be classified on the basis of being either primary, secondary, or tertiary. Let's remind ourselves what that means. 1 with the degree sign, again, is read primary. 2 with the degree sign is read secondary. And of course, 3 with the degree sign is read tertiary. Okay? Now, the simplest alcohol there is this one. This is the simplest alcohol we could possibly have, and this is methanol. Okay? Methanol is neither primary, secondary, nor tertiary. Well, one of the things I want you to be able to do is classify alcohols, okay, as being primary, secondary, tertiary. Let's remind ourselves how we do that. All one has to do is locate the OH group and then identify the carbon it's attached to. Okay? If that carbon is a methylene, a CH2, then this would be a primary alcohol. And recall as well that the symbol for alcohol is ROH. Now the reason it's called primary is because there's only one carbon, just one carbon attached directly to the methylene. Let's move over to the next one. Again, locate the OH group and the carbon it's attached to. In this case, it's a quaternary carbon, and therefore that makes this a tertiary alcohol. And using the previous analogy, You can tell that because we have 1, 2, 3 carbons attached directly to the carbon that bears the OH. Hence, this is a tertiary alcohol. The last example I have here would be a secondary alcohol for the reasons I've described. And that would simply be locate your OH, locate the carbons attached to. In the case we have a methine, CH, that makes it a secondary alcohol because we have 1, 2 carbons attached directly to the carbon bearing the OH. So this is something I want you to be able to do, classify alcohols, and it works this way. Now let's move down the page where I have sample problem 17.02. And here we're going to work on nomenclature of alcohols. Now these alcohols turn out to be a little bit different because you may notice we have more than one OH group attached to the carbons. Here we have 2 OH groups, and in the second example we actually have 1, 2, 3 OH groups. So let's name these 2 alcohols based upon things that we've learned in times past. The first thing I'd like to tell you is that since these OHs, there's 2 of them, that's going to make this compound a diol, okay? And as you can well imagine, this compound here will be a triol. Now I emphasize that for the simple reason is that you're going to have to include the term diol and triol in the name. Let's do this one here first. What's the parent? What do you notice here? Notice we have a cyclohexane ring system. Okay, that's important. And notice that we have OHs on adjacent carbons. Okay, well, we have to indicate where the OHs are bonded to the parent. Now this could be carbon 1, or this could be carbon 2, or you can go the other way, but you can see that this is an example of a 1,2 diol. In times past we even referred to this as a glycol. Now let's go ahead and name it. There's 2 different acceptable names. I'll show you both of them. But let's remind ourselves, just how big is this ring? What size is this ring? This is a 6 carbon ring, right? So you know that this is a cyclohexane derivative. So the name of this compound would be 1, 2 dash cyclohexane diol. Okay? 1,2 cyclohexane diol. The other aspect is the nature and the relative stereochemistry of the hydroxyl groups. Notice that they're in a trans orientation. So that means that you would have to place that in the name. So let me go back to the name that we provided, and let me write the word trans in front of 1,2 cyclohexane diol. This is a perfectly acceptable name, okay? And if this was the name that you provided on an exam or something like that, you would get full credit. Now, if we're looking at absolute stereochemistry, we would have to address that at each chiral carbon. So this carbon here is R, right? And this carbon here is also R. You may not remember how to do that. And if you don't, you can go back and look at chapter 5. But like I stated moments ago, this is sufficient. If you do use the absolute stereochemistry designations, then the name of this compound would be 1R, 2R, dash cyclohexane diol, right? And either one of these is perfectly acceptable. Okay? Let's jump over to the next example. Put a dash here to separate those apart. This one turns out to be very simple because it's simply an alkyl chain with branching OH groups. Now you may notice that it's symmetric, so therefore we could number from either end. And by doing that, we could say this is carbon 1, this is carbon 2, this is carbon 3, or you could go in reverse. But we know that the parent name here is what? It's propane. This is, in effect, a propane derivative. So using the previous example to help us name this one, what would be the name? You would simply call it 1, 2, 3 dash propane triol, right? 1, 2, 3 propane triol, and that would be sufficient. Now this compound here actually has a common name, and that common name is glycerol. Right? Glycerol is actually a byproduct of the saponification of fats, and it's used to make a lot of interesting compounds, one of which is called nitroglycerin. Okay, so those are just a couple of examples of nomenclature whereby we name the compound. And as I've always said, it's easier to draw a structure of a compound because all the elements of the name are already figured out. So let's go down to sample problem 17.03, where it says provide the structure of 3-phenyl-2-butanol. The important thing about this compound is that we have to recognize the parent name. And the parent name, the letters BU. And you know that means we have a 4-carbon unit. So why don't we go ahead and sketch a 4-carbon unit and then attach the requisite groups and or atoms to it. Okay, so there's my 4-carbon unit. Now let's address what's attached to that 4-carbon unit. This 2 tells us that we have what? An OH, because it would be 2-butanol. So it's incumbent upon me to recognize that that OH could go here if we're numbering left to right, or it could have gone there if we're numbering from right to left. Okay, and what else? Well, up front we indicated that there's a phenyl group attached to carbon 3. Now recall what phenyl is. Phenyl is a monosubstituted benzene. And folks, when you are asked to draw phenyl, you have the option of drawing the alternating pi bonds, or you can draw the delocalized sextet of electrons. It's entirely up to you. Let's finish this by providing the requisite number of hydrogens. We know that on the ends there are always methyl groups, so let me fill in 3 hydrogens there. And each of the interior carbons, carbons 2 and 3 respectively, are both methynes. So this is the condensed structure of 3-phenyl-2-butanol. I've taken notice that many of you enjoy or even prefer drawing skeletal illustrations. And if you would prefer to do that, it's perfectly okay with me. Let's draw a skeletal representation of the same compound using a zigzag orientation. So there's my 4-carbon chain. I would attach an OH group here, okay, and I would attach a phenyl ring here. So either of those is perfectly okay. So that's page 87. Let's continue with nomenclature by flipping over to page 88. If you go to the top of page 88, it asks us to provide a systematic name for the following phenol. Now you should recognize that this is the phenol because, why? Well, we have an aromatic ring with an OH attached. So therefore we have a phenol. No question about it. So it's simply incumbent upon you to recognize the names of the other atoms and or functional groups that are attached to this phenol. Here's the important thing. Recognize that we're going to name this as a phenol derivative, that by default that would be carbon 1. Okay? And you know that in this case we would go clockwise. This would be carbon 2, 3, and obviously carbon 4. And it's those positions where we have to name the other functional groups for atoms that are attached. So, what is the name of the functional group attached to carbon 2? It's called a cyano group. So in your name, you need the term 2-cyano. Okay? And what's more, you would need 4-chloro in the name. Now, you actually need these numbers, okay, in the name, but you don't have to have the number 1 because that's the default position for phenol. You've also learned that we have to alphabetize functional groups or atoms in front of the parent name. So, since both of these begin with a C, we would have to go with the letter H as being our first group that's bonded to the phenol. So the correct name here would be what? 4-chloro-2-cyano phenol. All one big word. Okay? And notice again, I don't have to use a number 1 because phenol has a default number 1 for the OH group. So this is just one example of a tri-substituted benzene that happens to be a derivative of a phenol. Let's do one more. Here it asks to provide the structure of 2,6-dimethylphenol. Okay, again you see that parent phenol. So that would be the best way to begin drawing the structure of this compound. Simply draw a phenol. Alright, there we have it. Now again, I'll leave it up to you whether you want to draw alternating pi bonds or the delocalized sextet of electrons in the interior. It's up to you where you want to place the OH. I'm going to go ahead and put mine up here up top. But realize there's 6 different positions that you could have placed that just as easily. And as we've said, this is default position number 1. Since you're drawing it, you can go clockwise or counterclockwise for the subsequent positions. Let me go clockwise. If I do that, this ends up being position 2. We know that a methyl group would go there. This is 3, 4, 5, and finally we get all the way around the ring to 6. So irrespective of whether you went clockwise or counterclockwise, owing to symmetry, you're going to end up with the same illustration that we have there. So this is an example of another tri-substituted benzene that has a parent as a phenol. For now, that does it for nomenclature. Let me move to section 17.2 entitled Properties of Alcohols and Phenols. Now when I say properties of alcohols and phenols, we're looking at both their physical properties as well as their chemical properties. Many of these things you've heard in times past, so you should be able to make a good estimation why the properties that we discuss are as they are. Look at sample problem 17.06. It says, why do alcohols typically possess higher boiling points than alkanes or alkyl halides of comparable molecular weights? Okay, and then it says, make a sketch to support your answer. Folks, the reason why, I'll cut to the chase, is simple. The answer is because of intermolecular, hydrogen bonding, H bonding, okay? That's the reason. But to really understand that, we need to make a sketch to indicate what it is we're talking about. Well, let's just remind ourselves before we do that, what is a boiling point? Okay? The boiling point is a physical property whereby you provide enough energy to reach a liquid vapor equilibrium at a given pressure P. In other words, you have to put energy in to create this equilibrium. But why would it take more energy for an alcohol compared to an alkane or an alkyl halide? Well, the answer is hydrogen bonding. You have to break the hydrogen bonds before you can get the compound to become a vapor. So let's show that. Let's make a little illustration that reveals that particular physical concept. So let me begin with the generic alcohol. I'll just use the letters ROH, okay? And let me put a couple lone pairs on there. And recall that, of course, that the oxygen is sp3, and therefore the preferred bond angle is about 109.5. And therefore, we have a tetrahedral arrangement around that oxygen. Now, what elements do we have here? Let's just make a little list. And in our little list, let's designate the electronegativities that are important. First off, we have a hydrogen, okay? Secondly, we have an oxygen. Thirdly, the R group would represent a carbon. You remember the electronegativities? Hydrogen is 2.1, oxygen is 3.5, and carbon is 2.5. So oxygen is very electronegative. It's the second most electronegative atom on the periodic table. And by virtue of having that type of electronegativity, the bonds are said to be polar covalent. So in this case, hydrogen would be what? Delta plus. Carbon would also be delta plus, whereas the oxygen is delta minus. That means we establish a dipole that runs right through here. A dipole that goes right through there. Well, if we have an adjacent alcohol, and let me just sketch one more over here. Recall that the nucleus of the hydrogen, or the proton, is exposed. It's very delta plus. And again, the oxygen is delta minus, the carbon is delta plus. What that facilitates, okay, is an attraction of the end of this dipole to the opposite end of the other dipole. Let me draw a dash between these two. Okay? What does that dash represent? That dash represents an intermolecular hydrogen bond. So in order for these to become a vapor, you must first break that bond, that hydrogen bond, and then you have to supply additional energy for these to move into the vapor state. that would not happen with alkanes or alkyl halides. So that's a physical property associated with alcohols. Let's move down the page to sample problem 17.07. Here we have a simple acid-base type of problem, and this is something we discussed back in Organic 1, particularly in Chapter 2. We're asked to label the acid, the base, and the conjugate acid as well as the conjugate base for this reaction. You may recall this is something relatively simple to do. You only have to take witness to what happens to the proton. As it turns out, this proton is acidic, and therefore it can be removed by a base. So automatically you know this is our acid. Okay? More specifically, it's the Bronsted-Lowry acid. But where did that proton go? It formed a covalent bond to water. So water here is functioning as a base, or specifically a Bronsted-Lowry base. So we have our acid and we have our base. Folks, the acid always becomes what? The conjugate base. And you can tell that partly because it bears a negative charge. What became of our base? It became the conjugate acid. Okay? So this is a designation of the acid, the base, the conjugate base, and the conjugate acid. Look at the second part. It says, in which direction is the equilibrium favored and why? Notice that we have an equilibrium here. What that means is all four of these things coexist inside a container. In other words, it's not 100% that way, it's not 100% the other way. There's an equilibrium that's been established, but which side is it favored? To do that, you have to look at the pKa values. These have to be given. So here we have a pKa of 7.15, and here we have a pKa, well, it's not given as a number, it's negative. Well, the implications are pretty clear. Folks, a pKa like this means what? It means that it is a weak acid. Okay? A negative pKa means what? That it's a strong acid. Once we've made those determinations, we can add to that. Folks, if this is a weak acid, that means that water is what? A weak base. Similarly, if this is a strong acid, this would be a what? A strong base. Now, what I'm going to do, rather than write strong base, I'm going to put the word stronger base. It's the strongest base in this system, but in reality, this particular base is not all that strong. Don't let that concern you. Just be able to designate acid, bases, and conjugates and tell me which direction the equilibrium would lie. Folks, when you put acids and bases together, what happens? They always get weaker. They don't get stronger because they partly neutralize one another. So in which direction would this be favored? Folks, it would be favored to the left. Okay? So that's our answer. Let me write that in. Favored to the left. Okay? Now, why? The answer is there. It's pretty simple. It's because you always favor the weaker side. Okay? Let me write that in up here. Weaker side, in this case the left side, is always favored. And it's simple, because when you mix acids and bases together, they don't get stronger, they get weaker. So that turns out to be a chemical property of a phenol. And of course this applies to alcohols as well. Let's do another problem that's kind of like that one. Question, why are phenols, okay, more acidic than alcohols? Okay, why are phenols more acidic than alcohols? Here's the answer. Let me provide the answer, and then let me provide a detailed explanation for why that is the answer. It says, upon deprotonation, what is deprotonation? That means when you lose a proton off of this oxygen. Upon deprotonation, phenols produce what? Resonance stabilized phenoxide ions. Okay? Do you see an example of a resonance stabilized phenoxide anion? There's one right there. That's an example. You could draw all kinds of resonance structures of that, and we'll do that on the next page. However, alcohols produce alkoxides that are what? Not resonance stabilized. And this goes back to something I said at the very beginning. Folks, if you have an alcohol, okay, bear in mind that that alcohol is bonded to an sp3 carbon. There's no pi bonds there. This carbon is entirely sp3. If you have a sufficiently strong base, okay, and I'll just use the term B, then what's going to happen? You're going to remove the proton, and you're going to have what's known as an alkoxide ion plus its conjugate acid. Okay? What's the big difference? Folks, unlike the resonance stabilized phenoxide ion, this is what? Not resonance stabilized. And therefore, it's much more difficult to remove this proton from an alcohol than it would be to remove the proton from a phenol. Let's move over to page 89. I'm about to finish up this section. Folks, this is something I want you to be able to do. Look at sample problem 17.09. Let's read that. It says arrange phenol, that's phenol, and the following para-substituted phenols, this one as well as this one, in increasing acidity. In other words, the least acidic to the most. Well, you're not given the pKa values, but you really don't need the pKa values. All you have to do is look at the groups that are attached to the aromatic ring. Now, I've chosen para, but you could have groups at the ortho or even meta position, or you could have one or more groups attached to the ortho, meta, or para positions. But let's keep this problem simple. What's the difference between A, B, and C? Well, if we sketch a hydrogen in here at the para position of phenol, and we can see that these three differ by what's in the para position. Here we have a hydrogen, here we have a nitro group, and here we have a methoxy group. Now you have to think back to chapter 16 in order to understand how this would work. Folks, recall that the nitro group is what? It's an electron withdrawing group. We use the letters EWG to indicate that. What is a methoxy group? Well, we could put in these lone pairs, and that helps us remember what that is. But this would be an electron releasing group. I believe it was page 77 of your chapter 16 notes where we talked about those things. Well, how does hydrogen compare to electron withdrawing group, electron releasing group? Well, For the most part, you can just think of it, okay, the hydrogen as being neither. Okay? Neither what? Neither electron withdrawing nor electron releasing. Okay. You can kind of tell where we're going with this. Folks, A is going to be right in the middle. Okay? And the others are either going to be more acidic or less acidic than phenol. Okay. Here's the rule. If you have an electron withdrawing group, that means it pulls electron density towards itself, and that's going to stabilize the incipient phenoxide anion. So folks, you have electron withdrawing group, okay, it's going to be more acidic. Alternatively, if you have an electron releasing group, it's going to force electron density into the ring after you've lost this proton. And therefore, these are going to be less stable. Okay? So this is how that works. I want you to be able to solve a problem like that. Okay, now let me give you a little more explanation on this. Folks, in your notes, you may want to sketch that in as well as this. Okay? These weren't provided in the original notes. But I think you can see where we're going here. Sample problem 17.10 reads this way. As shown in 1709, okay, let me, a little typo there, a phenol bearing electron withdrawing group, that's this one, is more acidic than one possessing electron releasing group. That would be this one. Sketch resonance structures of these respective conjugate bases of B and C to rationalize this fact. Okay? So folks, these are the conjugate bases of B and C. So let me just put a note here. Let me just call this one B prime. And let me call this one C prime to indicate that these are the conjugate bases of those two species. Now recall that the more resonance structures you can draw of a compound, the more stable. Let's do this. Let me place this pair of electrons between the carbons here. This pair of electrons there. Okay. This pair of electrons here. And of course the pi bond becomes a lone pair there. If you follow those 4 curved arrows, this would be the resonance form you're looking at. Now, this is extremely stable. Why is that? Look at all the conjugation you have. We're conjugated here. We're conjugated here. 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 And technically, we're even conjugated there and there. Alright? So you've really extended the conjugation. And what are the implications of doing that? It's very stable. Okay? It's not aromatic, which is even more stable. But among the non-aromatic illustrations you can make, this one's extremely stable. Let's contrast that with the one next to it, the one that I called C prime. C prime is the conjugate base of C. Let's use the same set of curved arrows to the extent that we can. Place that pair of electrons there. This pair of electrons here. Oh wow, look what we have now. Folks, we're bonded directly to an oxygen here, so I'm not able, okay, to extend the conjugation any further. All that I can do is put a lone pair on this carbon. Okay? Now, what matters? Look at the conjugation you have for this one. We're conjugated here and here, okay, and that's it. We don't have as much conjugation. Furthermore, this carbon here turns out to be a carbanion, this sp3. And furthermore, it's a negative charge right next to an oxygen. That's a very unstable situation. So folks, this one's very stable. This one here is far less stable. And the implications are very, very understandable in that it's always easier to remove a proton, to be much more acidic, when the conjugate base is stable. All right. Let's go ahead and stop right there. We'll pick up with the next section in the next video. Thank you.